So our last speaker of this session is Nai-Hui, and he's going to speak about quantum and minimum circuit size problem.
Thank you for having me here, and thank you for coming to the talk. And my name is Nai-Hui, and this is based on joint work with Ginny, Reize, and Chia. So here I just briefly review the minimum circuit size problem to make sure that we are on the same page. So for the minimum circuit size problem, the input is a truth table of some function f and some integer s, and want to decide whether there exists a circuit of size at most s that computes f. And here are some interesting facts about the minimum circuit size problem. First, the input size is actually 2 to the n. So an efficient algorithm for MCSP needs to run in time 42 to the n, so which means say 2 to the big O n. And we know that when the size is too small or too large, the problem is easy, because if it is too small, we can do brute force search and we can solve it in no time. And when the size is very large, then every function have a circuit with that size. Okay, and the complexity of MCSP is quite mysterious. It is an NP intermediate problem right now. So the problem is definitely in NP, because you can just view the circuit as a witness, and the verifier just check all the 2 to the n input to see whether the witness is consistent with the Boolean function. And MCSP is unknown to be in any subclass of NP. And we know that SDK reduced to MCSP via randomized reduction. And there's a conjecture said that brute force search is the optimal, or say is the best algorithm for the MCSP. And solving MCSP efficiently implies breaking one-way function. So that's why some people believe that if we believe that cryptography exists, then MCSP should not be in P. And then there are many results showing that the variance of MCSP is actually NP-hard or NP-complete. So here are some of the results. This is not an exhaustive list. And so, for example, the DNF MCSP is NP-hard, or DNF XOR MCSP is NP-hard. And then Oracle version of the MCSP is also NP-hard, and multi-output partial MCSP, depth formula MCSP are all NP-hard. And I think the difference between MCSP star and partial MCSP is that this one, you are just given the non-zero and the entry with the value to the as input, and this one you give the full Boolean table as the input. Okay, and one interesting about MCSP is that it connects many problems in theory of computer science. For example, for circuit, if you can show the MCSP is easy, then you can show like lots of circuit lower bound. For example, circuit lower bound for P to the NP, and also EXP not equal to ZPP, or you can show MCSPs in BQP. You can have new circuit lower bound for BQE, which is a quantum version of E. And then you can also have like learning algorithms. If MCSP is easy, then you can have a peg learning algorithm for like any function which has polynomial size circuit. And also you can show something about cryptography. As I mentioned, if MCSP is easy, then you can break all one-way functions and PRG. And also SDK reduced to MCSP, or suppose that we have an indistinguishable obfuscator, then set reduced to MCSP. So which means that stat and MCSP are equivalent under randomized reduction. And also you can have average case complexity. If you can show that MCSP is NP-hard, then you can show equivalence of worst case and average case hardness of NP. So this is not the exhaustive list of all the results corresponding to MCSP, because there are so many nice results that I cannot put in just one slide. But you can see the MCSP connects many problems in TCS. So the reason that we try to study the quantum MCSP is because that we attend the MCSP workshop in Stock 2020. And we are really inspired by by MCSP. Like the hardness is so mysterious and it connects many problems in TCS. And we also noticed that MCSP is asking the complexity of classical circuit complexity for classical objects. In other words, it is Boolean functions. And in quantum computing, it is very natural to consider quantum circuit complexity. And we are also very interested to know, quantum circuit complexity for quantum objects. Like, for example, we have quantum states, we have Hamiltonian, we have unitaries, and many quantum algorithms are trying to understand some properties about like states, Hamiltonians, or unitary. So in this work, in addition to consider classical object like Boolean function, we also want to consider quantum circuit complexity of quantum states or unitaries. So the goal is that we try to study a complexity of a problem and asking for the quantum circuit complexity of quantum objects. And we also want to connect quantum problems through the quantum MCSP. And as Jinin said in the paper, we try to understand quantum computing through a lens of meta complexity. So briefly, we define these three problems. So the first problem is similar to the classical MCSP, but instead of considering the classical circuit complexity, we consider the quantum circuit complexity. And for the unitary and state version, we change the targets. So here, the input is, for unitary one, the input is some matrix. And then for this matrix, we want to consider which the optimal quantum circuit they can output the same matrix. Or we consider the input as a vector of that represents an n-qubit state, or we just have many copies of the quantum states, and we want to know the circuit complexity of outputting the state. So these are all the three versions of MCSP we consider in this work. Yeah, question. So the second one, we have two versions. The first one, I have the full description of the state. So it will be a 2 to the n dimensional vector. And the second version is that you can have many copies of S. Yeah. And we don't know the relationship between them. I think it is easier to see that it is easy to see that if you can solve this one, and when you consider your T to be large enough, you can do a state homography to have a reduction. But other than that, I don't know any relationship between these two versions. But as I said, like the second version have more applications in the quantum computing. Yeah, we will talk about that later.
Is the state actually given?
They say you mean the second version?
Yes, actually in the first.
For the first one, so you will give a large vector. So like a Pascal vector for
coefficients.
Yeah, all the coefficients with certain accuracy. Yes. And because we are talking about quantum circuit complexity, I want to give you a very brief introduction about quantum circuit model. So quantum circuit model is similar to the classical circuit model. You have inputs, gates, and output. So usually we can describe the quantum circuit in this form. So you have quantum state as input. Usually you have two parts. The first part is input, like your problem, and you have some working qubits here to help you to do calculation. And you apply some quantum gates on it. And then you have quantum state here, and then you want to do some measurement to transfer the quantum information back to the classical information. So mathematically, any n-qubit state, which we can describe in this form, so which is summation of Cj and the Kj. So Kj, you can consider it as a, it's a 2 to the n vector, and the J's element is 1, and all the other elements are 0. And another thing about the Cj here is that Cj is a complex number, and the sum of square needs to be equal to 1. And usually for a quantum circuit, we have the input denoted as kx, so which means that the x element is 1. And then we have lots of ancillar qubits. They are all 0. And you can have polynomially many ancillar qubits. So these states will represent a 2 to the poly n dimensional vector. Okay. And how about the quantum gates? So for quantum gates, they are unitary. So it is a matrix, and you need to set it. You need to have this property, which is u dagger u equal to u dagger u dagger equal to u dagger u equal to identity, and u dagger is the conjugate and transpose. And for example, this gate we call it C naught. This is in this matrix. And for the Hadamard gate here, which is this one, 1, 1, minus 1, and you can easily verify that they are they are unitary that satisfy this property. And usually when we consider, quantum circuit, we need to consider all the gates are from some universal gate set. So which means that if I have the gate set, then I can approximate to any unitaries, we have. So, and in this talk, we just consider that we have a C naught and all single qubit unitaries. But for some of our results, we need to consider specific gate set. But for simplicity, you just consider that you can have any single qubit unitaries and C naught. And this is a universal gate set. You can use this gate set to approximate to all unitaries. Yeah. And in the last, I just talked a little bit about measurement. So the measurement, you just consider that you have some quantum state here, and you measure it in something we call a standard basis state. Then you can get index J with probability corresponding to the coefficient, like the Cj square. And the most famous example is shown in this cat, which means that the cat is in this state, like dead and alive, and you measure it, you get that with probability 1/2 and the live with probability 1/2. Okay. So that's about the quantum circuit. As I said, you have input state, quantum gates, quantum circuits. You have a quantum state here as output, and then you measure it, you get your output with certain probability. So there are several things that is very important about quantum circuit when we want to study MCSP. First, you can see that quantum computing is generally random and have error. So which means that probably we cannot directly study decision problem. It is more natural to consider promise problem, which means that our algorithm can give you like some answer with high probability, but not always correct. And then the quantum circuit is reversible because it is unitary. So you can have U, then you can have U dagger. So which help us to come up with search to decision reduction and also self-reduction for the unitary version and the state version. And another thing is that we have the ancilla qubits. And this ancilla qubits actually make the problem harder. So we cannot put like all these MCSP problem into MP. Instead, we can only put them into QCMA, which is a quantum version of marine answer. Okay, and there are various universal quantum gate sets, as I mentioned, and some of our results only hold for particular gate set. And another like a trivial observation is that if you have a small classical circuit for some function, which means that you also have a small quantum circuit for the same function. Okay, and any questions so far? So I will talk about the MQCSP first, which is that I want to consider the quantum circuit complexity of Boolean function. I want to consider the hardness of it, and I want to consider its connection to crypto learning and the quantum circuit lower bound. Okay, so here's a definition about the Boolean minimum quantum circuit size problem. I just call it MQCSP. So the problem is actually in QCMA. And why not it is in MP? It is because of the ancilla qubits, and I will tell you that later. And we can also show that multi-output MQCSP is NP-hard, which generalized the result by Elango, Love, and Oliveira in 2020. We found that we can follow their proof, and but with some additional technique, we can show that result also holds for the MQCSP. And we can also show that MQCSP SDK hard. And because MQCSP oracle can be used to break PRG, which is kind of like the PRG paradigm. If you have a MQCSP oracle, then you can have the quantum natural property that against quantum circuit. Yes. It is hard because we tried that one interesting QCMA hard or say complete problem. Okay, let's say this. If your circuit, you are not given the Boolean table of the circuit, you are given a circuit that represents that Boolean table, that truth table, then I can show that that problem is QCMA hard. So it's kind of like if you're a large circuit, I want to compress it to ask you whether there's a smaller circuit for the large circuit.
And it's multi-output.
Multi-output or single output, I can show that they are QCMA hard. But I don't know whether I can put it inside QCMA. That problem is even harder than QCMA, I think. Yeah. But for the truth table one, I don't know how to show it as QCMA hard. Yeah.
Sorry, you said you're talking more about these ancilla, why ancillas are
no. So the question is whether we can show MQCSP is QCMA hard.
No, I'm saying that. Okay, yeah, I don't see why if you don't have ancillas, it's in NP.
Oh, yeah. Next slide we can show that. Yeah.
So
yes,
the reason why it's SDK hard is that it's a natural property.
Yeah, because of the natural property.
Yeah.
Yeah. So
it has all the other, in addition to being SDK hard, it has all the other advantages of natural property.
I think for that result, you don't need, you just use the natural property, then you can show
right.
that.
So I mean, so you also get like de-randomization and so on if MQSP is easy.
Oh, you mean the PRG? Yes. So here I will show you like why MQCSP, is QCMA, but we start from try to put it inside the MP first. Okay. So suppose F has a quantum circuit with size at most T, then we just let C be the quantum circuit that computes F without using any ancillary qubits like here. And then the certificate or say the witness is the circuit C. And then, and we cannot run C because V is a classical algorithm in MP. But on the other hand, since we allow V to run in 2 to the big O n time, right? Because the input size is 2 to the n. So actually, we can try to just compute a unitary that corresponding to the circuit C. Okay. And then given the unitary, you can try to see whether the unitary is consistent with the truth table. So in this way, you can put MQCSP inside MP. If your circuit is only work on the n qubits. Okay. So it looks like this is kind of like this just follow the classical proof for like MCSP is in MP. But why if we allow like poly and ancillary qubits for our circuit? So now you have poly n qubits, and then like the corresponding unitary will be a 2 to the poly n unitary. So the dimension will be 2 to the n times 2 to the poly n times 2 to the poly n, and the verifier even cannot be able to write down all the unitaries in 2 to the big O n time. So this approach does not work directly because verifier doesn't have sufficient time to compute the unitary about C. The number of ancillary qubits should be unknown. So the problem is just the Boolean type of F and the corresponding integer S, and you can use arbitrary many the ancillary qubits, but it needs to be polynomial in n to compute your function.
Or it does need to be smaller than S.
Yeah, it needs to be smaller than S. Correct.
Okay.
Yeah. Or yeah, just smaller than S is correct. Yeah. I think it also depends on how many things you can allow. If you allow like more things, it can depend on some constant times S, something like that. Yeah. But like we can put it inside QCMA. The reason is that if I come up with the circuit, then I can just, the quantum verifier can just implement the circuit, and then we can compute everything, right? So in this way, we can put it inside the QCMA complexity class. So good. So we can skip this one. And then I want to talk a little bit about the MQCSP and its connection to other problems. So for example, if we have quantum secure one-way function, the MQCSP is not in the BQP, and this follows that you can use MQCSP to break OPRG and then to break BRG, and then you can use it to break the one-way function. And we can also show that if you have a post-quantum indistinguishable obfuscator, then MP is not in co-RQP, implies MQCSP is not in BQP. So co-RQP is the quantum polynomial time with perfect soundness and the bounded error completeness. However, the other direction is unknown because MQCSP is unknown to be in MP, so we cannot prove the other direction. But in the classical proof, actually you can prove the equivalence and such that you can say that is equivalent to MCSP under randomized reduction. And another thing is that you may try to replace the MP here, but if you want to replace the MP here to be QCMA, it's a little bit mysterious because I don't know which complete problem we can try to solve by using the MQCSP oracle. But like those are like interesting questions we can study. Yeah. So in other words, like here, what we want to know is that suppose we know the hardness of MQCSP, like whether it is easy or hard, can we use it to help us to build cryptographic primitives? Or we can say like cryptography implies the hardness of MQCSP. Okay. Yeah.
You want something weaker than one way or weaker than quantum secure one way?
Yeah, so actually, like we are trying to say whether we can use the MQCSP to come up with something we call a pseudo-random states, which means that you have an efficient person generate some quantum state that is indistinguishable from the random quantum state. And we can, and actually there are several results showing that this PRs might be a, how to say, a weaker assumption than the quantum secure one-way function. Yeah, so that's an interesting. Yeah.
About the difference between the first and the second result.
The first and the second result. Okay. So the first result show that like you can use MQCSP to break one-way function, and this result you need the quantum IO to show that.
To show the same.
Yeah.
To show the same thing. Now I'm not sure, but does post quantum IO imply post quantum one-way?
Well,
I think William Kretschmer has a result where they separate that as well, I think.
so it did.
William Kretschmer. Yeah.
So it kind of depends. So the IO is not monotone in complexity.
Yeah,
because of
let's
like
assume that P different from NP.
But then that's kind of contradicting what the whole assumption here, because they're just saying you do have a quantum algorithm for all of NP, or if we're just trying to argue that we don't have a quantum algorithm for all of MQSP. Sorry.
Yeah, so if you assumed that P did not equal NP, then the conclusion, it's not exactly trivial, but it's the sort of the MQCSP is not in BQP is sort of similar in flavor to the P is not in NP. So like if we're assuming that already, then we don't necessarily, like it doesn't necessarily make sense to argue for it. So
Yeah.
Does that make sense?
Yeah.
So yeah. And okay, we can also like generalize the result in the CIKK 16, like to about like quantum packet learning. So actually what we can show is that if you have an efficient classical packet learning algorithm for BQP/poly, then it is equivalent to say there exists an efficient randomized algorithm for MQCSP. Or you can consider the quantum learning algorithm. If you have efficient quantum learning algorithm for packet learn circuit class C, so here the circuit class can be a quantum circuit class or classical circuit class. Then there is an efficient quantum algorithm for the C MQCSP. So the second result actually mainly follows the technique in the Arunachallam et al. In 2019, presented by Alex yesterday. So the main idea is that if I have a MQCSP oracle, then I can have a quantum natural property against quantum circuit complexity, quantum circuit class. So start from there, then you can generalize the classical result to the quantum setting. So in this way, we can relate quantum learning theory into the hardness of MQCSP. So you can also have the connection between MQCSP and the circuit lower bound. For example, if MQCSP is easy, then you can show circuit lower bound for BQE and the BQP to the QCMA. And the idea is still follow that quantum natural property against quantum circuit classes. And we also need some diagonalization lemma for the quantum circuits. And we also have the hardness amplification, hardness magnification, and the fine-grained complexity. So like those results, you need to somehow prove some quantum versions of something about the PRG. Like I think the amplification one, we need to prove that the quantum security of the Impregasso and the Wiggerson PRG generator. And then we also need a quantum secure Nissan-Wiggerson generator. And for the magnification result, we need a quantum anti-trickle lemma for the function. But like those results, usually you can follow the classical results and try to fix the issues there when you consider quantum circuits. Okay, and then I want to spend a little bit more time on the quantum objects. So for quantum objects, here we consider unitary or quantum states. So here when we said that we have a circuit that computes U, which means that for all the states, if you consider inner product, their inner product is close to 1. Or when we say about we can compute the state S by using C, which means that start from 0, C up around 0, the inner product between A and C are close to 1. Okay. And then we will still first show that these two problems are in QCMA. We can also show some reductions about these two problems. Like these two problems have search to decision reductions, and also the SMCSP one has something we call the self-reduction. And I will also briefly say some application about these two problems in quantum computing. Okay, so first of all, SMCSP is in QCMA. So still we start from the witness. The witness is just a circuit of the size, at most T that computes S. And we also have a verification. So for the verification, we use something we call the swap test. So for the swap test, which is this circuit, you have two states, phi and psi input to a circuit. And the probability that first qubit output 0 will be 1/2 plus the inner product of the two states, right? So if the two states are equivalent, which the inner product will be 1. So the probability that you will output 0 is 1. And if the two states are orthogonal or very different, then the probability that you output 0 will be 1/2, around 1/2, right? So using a swap test, you can check whether the two states are close, or they are orthogonal, or they are far. So for the SMCSP, what we do is that, okay, after the verifier got the circuit, you just prepare the state. State C of 0, and you also need to prepare the state S of the input. So the first thing is that if you have a vector of n qubit state, which is a 2 to the n vectors, then given a classical description, you can prepare the state using 2 to the n control rotations. So you just need the big O to the n time, then you can prepare a state from B. And the second version is that you got arbitrary many copies of S, right? So in this case, because you already have the S, you don't need to prepare the state by yourself. And then you just run this two, you just fit these two states into a swap test. And then you do this test many enough times, then you can distinguish whether they are close or they are far from each other.
What does it mean for this problem to be in QCMA in the input 2 case where your input is not even, doesn't even have a
Yeah, so that's a good question. So for the first input, you can say it is pro minus QCMA. For the second one, right now you only have the quantum states as input, so it is not a QCMA problem. So you can just say that it has a QCMA proof, or you can define some complicated case which is called state QCMA or something such that the input of the problem is quantum states and try to decide something. Yeah. So actually in our paper, we don't say it is in QCMA, we just say that we have a QCMA protocol to certify the result. Yeah. And then the second thing is try to prove the UMCSP is in QCMA. So a naive approach is that you still run a swap test for all computational basis states. Say I have C and U, and then you just try to check whether they are equal from 0 to 2 to the n minus 1. But this does not work because they may differ on superposition state. Like it is possible that C with input 0 plus 1 give you 0 minus 1, but U is still 0 plus 1 give you 0 plus 1. In this case, you have no way to distinguish them. And also we have to consider ancillar qubits. So there may be some entanglement between your output qubits and ancillar qubits. And that will introduce another phase to to your output. So this approach does not work. So we need to introduce a new test we call the coherent test. So you just do swap tests on all states of the form. 1 over square root 2 of A plus B. And here A, B are arbitrary computational basis states. And our key lemma shows that suppose the circuit passed the standard basis test here, and also the coherent test, then you can show that actually they are correct on O, A, B, and also this part is the ancillar qubits. The state on the ancillar qubits are almost the same. Okay, and after we have these two tests and then have this lemma, we can show that actually if you can pass these two tests, then the unitaries and the circuits are the same, or they are close. Okay. And then we can say something about the search to decision reduction. So we know that it is unknown whether MCSP has search to decision reduction, right? So Actually there are some research showing that okay, if MCSP is search to decision reductions about some variants of MCSP, like the gap version MCSP, average MCSP, or MFSP, so which is a formula version. And also this one showing that if the worst case MCSP is in BPP, then you have a randomized polynomial time algorithm for finding an approximate optimal circuit. And also there's some relativization barrier for deterministic search to decision reductions for MCSP. Okay. So the main idea here is that because unitary is reversible, so we can try to uncompute the gate from U. So here is a reduction. So the goal is that you are given U and then oracle for UMCSP, and you try to find the quantum circuit C such that use the UMCSP oracle to help you to find to find a circuit. So here we first use the UMCSP oracle to find S equal to quantum circuit complexity of U. And then we start from I equal to 1, and then we just do some while loop. So what the while loop do is actually that when you have, in the first step you have U, and you just get some G1, and then you uncompute U from G1 dagger. And then you use the MCSP oracle, try to check whether the circuit complexity decrease or not. If it decrease means that, okay, the guess I made is correct. So I can say the first get is G1. And then I can set this one to be a new U. And then I try to come up with the second G2. Okay. And then you uncompute G2 from U G1 dagger. And then if the circuit complexity decrease, I know that my guess is correct. Then I can put G2 as the second gate. And I can do this iteratively. In the last, I can get G1, G2 to GS, which is the circuit we want. Okay. And in this way, you can have you can have a search to decision reductions for UMCSP. Yes.
And this isn't something special about quantumness here. This is just because it's a reversible circuit. Like
yeah, this is because it is reversible.
Yeah, the same reduction would work.
Yeah, the same reduction work for the classical. If we have a classical reversible circuit, like using the TOEFL. Yeah.
Where you're using reversibility is that the number of inputs isn't implicitly growing. So it's
the number of inputs doesn't growing.
So like you could introduce a new gate. Oh, I see. But then it would be only on partial inputs.
Yeah.
Because you wouldn't have all the possible. It would be a promise problem.
Yeah, that works for partial MCSP. Yeah. To give it.
Yeah.
So for this reduction to also work for the SMCSP problem. So this one is a unitary, but you can do a similar thing for the SMCSP. But I want to give a note about this reduction. So the reduction right now only hold if we don't consider ancillar qubits. So in particular, so suppose the input is U is a 2D by 2D matrix, then our circuit is also for n qubits without any ancillar qubits. So the main reason is that if I consider U and then I can compute it by from a larger unitary, then in addition to guess the the gate G1, I also need to guess like which part of I also need to guess the unitary on the ancillar qubits, right? So the main reason, like because I don't have a full description about a unitary or states, so I need to make some guess about it. And then, so to the best of our knowledge, if you don't have too many ancillar qubits, then you can just use the epsilon net. Then you can still do a search to decision reductions. But if you have too many ancillar qubits, then this reduction doesn't work because it is inefficient. So
the reduction is for the unitary version or for the state version as well?
For the unitary version and the state version.
For the unitary version, does it make sense to have more ancillars then?
For all ancillar?
Like when you have the unitary version,
yeah.
Do you consider that the state, the circuit that implements it could also act on more ancillar qubits?
I think it is possible, right? Or you need to prove that like additional ancillar qubit doesn't help you to compute the unitary efficiently. Did that answer your question?
Yeah.
At least for the state version, it is quite clear that if you have more ancillar qubits, it can help you to prepare some states efficiently. Yeah. But the thing is that, you know, like we don't know how many MCRs you can use for your, to prepare some unitaries or states more efficiently. So that's a important thing about this search to decision reductions. So too many NCR qubits, our reduction fail. And if the number of NCR is small, then I think you can use epsilon there to complete the proof. Okay. And I just spent a little bit more time on the self-reduction for the SMCSP. So why we call this SMCSP the self-reduction is that if you can compute the circuit complexity of n-1 qubit state, then you can use this algorithm to approximate the quantum circuit complexity of an n qubit state. So like this formula. So this is the circuit complexity of psi with the approximation ratio epsilon. And then this one can be upper bounded or lower bounded by the circuit complexity of an n-1 qubit state, psi 0 and the psi 1. And here, psi 0 and psi 1 is defined as here. So for any n qubit state, we can use the Schmidt decomposition to decompose it into 0 psi 0 plus 1 psi 1. So this is the standard way to to decompose the state into two systems. And then what this reduction do is that why this this bound is hold is that okay, we can just consider that we can estimate everywhere A1 by by have sufficiently many copies of psi. And then we just consider two cases. The first case is that either A0 or A1, which is very small. So which means that psi is close to the other. For example, if we say that A1 is very small, which means that psi is close to 0 and the psi 0, because this branch is almost negligible. And then in this case, the circuit complexity of psi can be bounded by a circuit complexity of psi 0, right? So you can have the bound by just using 0 and the psi 0. And the second case will be non-trivial. So the second case is that both A0 and the A1, they have sufficiently large coefficient. So the lower bound is that okay, if I give you psi and then you just measure it like many enough times, then you can come up with psi with desired I with high probability, right? So in this way, you can just have many enough. Like here, I just said that this should be big omega epsilon. So just measure it many enough times, then you can have psi. And how about the upper bound? So for the upper bound, we need to use the following circuit. So this circuit is that okay, if I have C1 and the C0, they compute psi 0 and the psi 1. And then I can use this control rotation to help me to construct psi. And then if you want to have a control rotation of specific circuit, you need to have some constant blow up. So that's why we have an additional constant blow up layer here. Okay. So in this way, you can have an upper bound and lower bound for the circuit complexity of psi if you know how to compute the circuit complexity of psi 0 and the psi 1. Okay. And in the last, I talk about the application. So one thing is that actually we have another reduction that can reduce the gap version of MQCSP to UMCSP. And based on this reduction, we can generalize many applications of MQCSP to UMCSP. Like you can also use UMCSP to invert one-way function to harness magnification, quantum circuit lower bounds, and so on. And for the SMCSP, if you just consider a state version, which is that you are given many states instead of a full description about the quantum states, then you can use it to break quantum pseudo-random states, or you can use it to estimate wormhole volume under the ADS-CFT correspondence equal to V conjecture. And the dictionary map is computable, something which people assumed in the quantum gravity. You can use this one to estimate the complexity of certain quantum state, and the complexity of that quantum state actually corresponding to the wormhole volume in the ADS. So we can also use this one to sustain some problem we call sustained state tomography problem. But that one you also need to use the search to decision reduction. Yes. Okay. So that's all the results we have in the work. And I just want to give a quick conclusion and some open questions. So the quick conclusion is that, okay, we studied harness and applications of quantum MCSP. We studied Boolean unitary states And we also we only consider quantum circuit complexity of them. And here are some open questions that we can consider. Like right now, we only say that those problems are in QCMA, but we don't know whether they are NP-hard or QCMA hard. So it is interesting to know whether it is possible to put these problems inside NP, or can you prove NP-hardness of these problems? Or say, can you prove is QSDK hard or other subclass hard? And also like the hardness of quantum MCSP, we want to know whether it connects to some quantum cryptographic primitives that just used recently, like quantum pseudo-random states, EFI, or one-way state function, and so on and so forth, or connected to the quantum commitment and so on. And we also want to know whether there are reductions between quantum MCSPs. So like we only know MQCSP reduced to the unitary version, but we don't know other reductions between different versions. So we really want to know what's the relationship between different versions of quantum MCSP. And we also want to consider a worst case to average case quantum reductions for MCSP, or consider hardness average case quantum MCSP, and also the fine grained complexity and the quantum MCSP. Like for example, if I assume MCSP is hard for a specific runtime, then can I show that other problems are hard for, above some lower bound? And also other quantum meta complexity, like quantum version of Kolmogorov complexity. Yeah, and that's all. Thank you.
Questions?
So do you have a feeling of whether it should UMCSP should be QMA hard, or do you think it should be?
I think so. As I said, I don't think it will be QCMA hard. So because as I said, so I can only prove that a harder version is QCMA hard, and I don't know whether it will be. Yeah, so I just said it is hard to say. But right now, I still think even it is still very hard to prove that it is NP hard. So probably the first step is try to see whether it is NP hard, and then go to QCMA hard. Another thing is that we don't have many QCMA complete problems there. So that's another reason that it is hard to imagine what kind of problems can be easily reduced to to QMCSP. Yeah.
Another question is that do you know if your RS and MCSP star so translates to the quantum setting, or?
I mean the MCSP star one. I remember that there are some issues there, but I forget because we tried the multi-output MCSP and the MCSP star 2 versions. I remember the your MCSP star result, we haven't been able to successfully do down that, but I cannot recall the reason right now.
Okay.
Yeah.
Have you considered like the state version where you have mixed states instead of pure states? Because it seems harder to put into QCMA, right?
The mixed state version.
Yeah.
I remember. So I remember like in Scott Aaronson's lecture note, it says that if you consider the mixed state and you allow measurement in your circuit, sometimes you can use a very small circuit to compute the high complexity mixed state. Okay, the quick question is that we haven't considered that kind of state version, but I think we can try. Yeah.
Questions? Thank you. So I think we are convening at 2 o'clock.